Alright, so welcome back. Today we're going to take a look at a little bit of how we carry oxygen. So we've talked about hemoglobin already when we were back doing blood cells and the red blood cells. We know that red blood cells are mainly filled with hemoglobin, and hemoglobin is really there to carry oxygen. Each hemoglobin molecule can carry up to 4 oxygen molecules based on the active sites and where that iron is at. One of the things that we can see is that depending on you looking at your blood, you can see how much of your hemoglobin is bound up. A lot of times we talk about our percentage of oxygen saturation of hemoglobin. So PO2 being the partial pressure of oxygen is one of the biggest things of that. And again, as long as we have a high enough partial pressure, we should be able to saturate all of our hemoglobin. One of the things that we're going to notice with this is every time an oxygen molecule binds to hemoglobin, it actually makes it easier for more oxygen to bind. So you get one on there, it makes it easier for the second one, easier for the third one, and so on. And what that gives us is this nice S-shaped graph where it takes it a little while for that hemoglobin to saturate, but then it gets really steep, and then as we approach getting it fully saturated, it plateaus out and really levels off on it. So you get this nice S-shaped graph. The other thing that means is little changes in partial pressure can give us very big differences in saturation. Like it's showing there at 60 millimeters of mercury, you can saturate oxygen, the hemoglobin, about 90%. Once you get above that, then it's going to be each bump up is going to just lead to a smaller change. So you can kind of see the idea right here. So if you look at A, that would be about 20 millimeters of mercury, and you can kind of see in that one it's about 35% saturation. Just doubling that does actually more than double this. So you go from 35% here to almost 75% by just going up 20 millimeters of mercury. You can see once we get above 60 millimeters of partial pressure, it's about 90%. And then as you're getting up above that 100, you're getting close to that 98% saturation levels on this one. So again, this S-shaped curve where you get a little bit on here, it makes it way easier for it to get on here. And as we really start binding up that hemoglobin completely, much larger changes in the partial pressures lead to very little changes in saturation. One thing I do want to point out is if you look at partial pressure, what is the partial pressure normally in the alveoli? It's somewhere around 105 or slightly there above, which means under normal conditions at sea level at that 760 millimeters of mercury, where should we be on this graph? We should be somewhere right around here where your hemoglobin is almost fully saturated. So at that 98, 99% on this. And that's part of the reason if they put the little pulse oximeter on you, you usually will read 98, 99. What that thing is actually doing is there is slightly color differences in there as that goes. So when they put the little light there reflected, they have a sensor that is looking at the reflected light back, and depending on how saturated your hemoglobin is, you're going to get a slightly different wavelength coming back to that, and that's how they actually measure that with the pulse oximeters. So with these ones, you can kind of see how the effective altitude would be at about 5,000 feet of altitude, and that's really where it really starts making a difference. It's about a mile up is where you'll start seeing physiologic differences in your hemoglobin saturation. So below 5,000 feet, the partial pressure change is not really big enough to start reducing that saturation. But you can see at about 5,000 feet, the alveolar partial pressure is about 81 millimeters of mercury. And if we went back to the graph, that's now seen at about 95%. As you can start seeing as you start going higher and higher, so let's say you're climbing Denali in Alaska, you can see as you start getting above 17,000 feet, that partial pressure now is getting down to where if you're not doing supplemental oxygen, you're only going to have a hemoglobin saturation of about 75%. As you start getting below 70%, that starts becoming dangerous to life. So you can kind of get the idea as you start getting higher and higher altitudes why, for example, climbing Mount Everest, which gets up to 29,035 feet, you can start having issues with altitude sickness or other things. As you get these really low levels of partial pressure of oxygen, it means you get really low saturation of that, and because of that, organs that you would want to have good oxygen delivery to are just not going to get it. So a lot of times it's going to be headache and nausea, but as we start getting worse and worse, you can get these issues with pulmonary and cerebral edema and having life-threatening conditions if you stay at altitude for too long. So one of the things we're going to see is as that leaves the lungs and is in the bloodstream here, as it's getting to those capillaries, you're going to see it should be really high saturation. We are going to reduce that saturation a little bit as it goes through those systemic cells and delivers stuff to the muscles or whatever else. So after you've dropped stuff off at sea level, it's going to be about 75% saturation. Again, showing you that only about 25% of that oxygen is actually being released as we drop stuff off at the tissues. Again, this is a reserve. So if we need, under increased metabolic demands, more oxygen, the fact that we don't drop all of it off currently means we can tap into that when the higher level of need arises. And again, that's referred to as oxygen reserve. And it's just that fact that a lot of oxygen remains bound to hemoglobin. And again, as we get more and more demand for this, we can drop more and more of it off. Again, if you're exercising, really needing more of this, we're going to lead to these larger offloading at the tissues, again, which would drop that partial pressure of oxygen on that hemoglobin that's making its way back up to the lungs. One of the things that's interesting, and it's like, and again, that class that I'm going to teach next fall, we talk a lot about some of these physiologic changes, but there are certain things that make it easier for the tissues to drop off that oxygen in a tissue that is being more active. One of the things is that tissue is working, it's going to increase that temperature. Increased temperature decreases the affinity of hemoglobin for oxygen. It makes it easier to drop off that oxygen. So when a muscle is being really active and it's warmer, it's going to lead to increased offloading of oxygen at that tissue. Same thing with hydrogen ions. If you get this increased acidity there, again, lactic acid, other things like that, building up acidity there, increased carbon dioxide also will increase acidity. This is going to lead to, again, increased offloading at these tissues where this is happening. They refer to this as the Bohr effect, but the decreased affinity for oxygen and hemoglobin and increased release due to those increased levels of hydrogen ions at the tissues. Another thing that happens is when tissues are requiring more oxygen, they will release one of the byproducts of doing glycolysis is this product called 2,3-BPG. If you're starting to go anaerobic, you're going to kick out more of this, and again, it will cause increased offloading of that oxygen at these tissues where this is being produced. Certain hormones, like it says there, can increase the amounts of this being released and therefore increase the metabolic activity in that tissue, increase offloading of oxygen at that tissue. Things like epinephrine, growth hormone, testosterone are all going to do that. Again, making that stuff more available to those tissues that are releasing this 2,3-BPG. As we build up more carbon dioxide, and especially carbon dioxide, we'll see in this last little show after this one of the ways we carry carbon dioxide is actually bound to hemoglobin. They call that carbaminohemoglobin, which is just a fun word to say. Has a nice little flow to it, carbaminohemoglobin. It kind of does that little... Anyways, when you get more and more carbon dioxide binding to the globin portion of hemoglobin, it decreases the affinity of that hemoglobin for oxygen and therefore is going to increase offloading of that. The other thing that's kind of interesting is as we unload oxygen, it actually increases the ability of that globin portion to carry carbon dioxide, which is called the Haldane effect. But the main thing this makes sense. If you offload more oxygen, it means that you should be able to pick up that we're probably producing more carbon dioxide, and therefore the conformation change by offloading more of that oxygen is going to increase your ability to carry that carbon dioxide back out. What this does to our curve, so if we remember that little S curve there, anything that's going to increase the affinity for hemoglobin, we're going to see it's going to actually shift that left. So it's going to shift it up on that curve. So things like decreasing temperature, decreases in hydrogen ion concentration are going to increase the affinity of hemoglobin for oxygen. and because of that, makes it hold on to it a little bit better. Things like increased temperature, increased hydrogen ion, increased carbon dioxide, 2,3-BPG, all these things do what is called right shifting of that hemoglobin curve, which means at a higher partial pressure, it's going to be less saturated, meaning it's dropping off more oxygen at those tissues when it's shifted to the right. And you can kind of see it on the graph right here. Increased acidity, so lower blood pH, it shifts it to the right. And again, at 50%, this one would only be 60% saturated with that higher acidity, where it's going to hold on to it better under normal conditions. So at that 50%, it might be at 75% here, where at a really alkaline pH, it might be at 85% under that same 50 millimeters of mercury partial pressure. So you can see a right shift makes it less affinity, lets it drop it off easier. A left shift makes it hold on to it better. And again, neither one of these things necessarily mean it's a good thing or a bad thing. A right shift or left shift, neither of these are actually a good thing or necessarily a bad thing. It's just kind of showing you under conditions where you want more offloading, it's going to decrease that affinity for it to hold on to it. Again, the whole idea with hemoglobin is it is a delivery truck. We don't want a delivery truck that just holds on to its product and doesn't drop anything off. So again, having a higher affinity is not necessarily better. Having a lower affinity is not necessarily bad. But again, you can see carbon dioxide, increased partial pressure of carbon dioxide. So your tissues are being more active, making more carbon dioxide. It decreases the affinity of that of hemoglobin for the oxygen. It's going to increase offloading at the tissues. You can see the same thing with temperature. Increasing the temperature in the tissues, more offloading. Less, it's going to hold on to it better. Increase 2,3-BPG, going to increase the offloading. Less of that, going to increase the affinity. So again, to me, knowing what a right shift and a left shift is, and again, knowing some of these different factors like acidity, like carbon dioxide, like 2,3-BPG, what do they do to these curves, and what does that mean in terms of offloading at the tissues? That's all stuff that to me is key for understanding for our exam. And especially if you become interested and decide to take my course, that's one of the things that we will talk about a lot on this stuff here is respiratory changes in terms of how we carry this, and some of the changes that if you exercise over time, what it does to some of these things here, it makes you actually more efficient at offloading oxygen at the tissues. It's really kind of some really neat, wicked physiology. Another thing that's kind of interesting is fetal hemoglobin actually has a slightly higher affinity than maternal hemoglobin, which again, to me, makes sense. You want, at the placenta, favoring of oxygen leaving the maternal hemoglobin going to the fetal hemoglobin. Having that higher, slightly higher affinity, slightly left shifted curve means that the fetus is going to be able to draw more of that oxygen to its hemoglobin. What is also can become an issue is, and we've talked about carbon monoxide poisoning before, but carbon monoxide, CO, hemoglobin has about a 200 times greater affinity. So for that versus oxygen. What that means is a lot of times if carbon monoxide gets onto hemoglobin, it's not permanently bound, but it almost acts like it because the affinity is so high for it. It grabs onto it, and what that does is that outcompetes oxygen getting in there. So again, if you get too much carbon monoxide into your bloodstream, it's going to preferentially bind to all that hemoglobin, and you're going to lose your ability to pick up oxygen, carry it someplace, and drop it off because that carbon monoxide is almost permanently bound into it. So part of the good reason to have the carbon monoxide detector, you can't smell it, you can't taste it, you just get nauseous, get a headache, you pass out, and then you don't wake up. So not a good thing to have happen. Some other interesting things here, as hemoglobin picks up oxygen, it also picks up nitric oxide. When oxygen dissociates from hemoglobin in the tissues, it causes nitric oxide release into the tissues. Nitric oxide is a vasodilator, so what's kind of interesting about this one is when oxygen levels are low and the release of oxygen happens quite a bit in there, it also assists in that O2 delivery by acting as a local vasodilator where tissues need more oxygen. So kind of neat that hemoglobin, like it says there, carries its own vasodilator. The lack of oxygen is a lot of times what we refer to as hypoxia. So having this low O2, and it can be due to a number of different things. The first one to me is always kind of funny, hypoxic hypoxia. That's low oxygen due to the fact that you don't have much oxygen. So low oxygen due to the fact that there's low O2 in the lungs. So the environment you're in is hypoxic, therefore you're hypoxic. So you don't get very good O2 saturation. So being at altitude, being in an area where they're being suffocated, for example, would be examples of hypoxia. Anemic hypoxia is the idea that there is plenty of O2 in the atmosphere. You just have an inability to carry it due to low numbers of red blood cells or incorrect hemoglobin, things like that, different hemolytic diseases. Stagnant hypoxia or ischemic hypoxia, this is plenty of in the air, plenty of ability to carry it, just your blood flow is not moving. So heart failure, blood clot, something that's not letting that blood travel to the area that needs it, makes it hypoxic. And finally, histotoxic hypoxia. This is tissues can't get oxygen because there's some type of poison, something like carbon monoxide, cyanide, things like that, where you're not getting it being able to bind to those tissues because something else has inhibited it, some type of toxin. So we have one more show to go on this one here. The last thing we'll be talking about is mainly a little bit of regulation of breathing, what regulates it, along with how do we carry carbon dioxide. So I'll see everybody for one last one for this next time, and then we're taking a test.